Hello everyone. Today in this video we're going to speak about the fundamentals of computers, that is transistors, logic gates, and combinational logic circuits. So let's start. Transistors. Transistors are the fundamental components of all computers, and more specifically their CPU, the brain of a computer. But simply they are just switches in an electrical circuit. They either block or allow the flow of electrons. The material which the transistors are made of is called a semiconductor. So semiconductor, it's a material that depending on the circumstances can conduct electricity like metals or act as an insulator like plastic. So let's examine the structure more thoroughly. So basically and more commonly semiconductor is produced of silicon atoms. uh, about silicon atom, it has four electrons in its outer layer that can be connected with four other silicon atoms in a crystal. However, a semiconductor is a doped silicon crystal. What does it mean, doped? Doped, it means when we replace one in a million silicon atom with phosphorus atom, which has instead of 4 5 electrons in its outer layer. So this additional electron can flow freely in the crystal and enabling it to conduct electricity. This electron creates a surplus of a negative charge and therefore this type of semiconductor is called n-type. But what if we replace the phosphorus with something that has little and less than four electrons in its outer layer? Some element like boron, it has three electrons in its outer layer. So the fourth place when there should be electron connected to the electron with the silicon atom, there is a hole. This hole is basically an means the absence of electron, which means the positive charge, and that's why it's called p-type, p4 and positive. So what if we position these p-type and n-type semiconductors together this way? So in the era of connection, there is something special layer that is called depletion layer. Here, holes from the p-type semiconductor are filled with the surplus electrons from the n-type semiconductor. Uh, and by creating this layer, the electrons from n-type semiconductor doesn't possess enough energy to jump over it and fill the holes. And if we connect this structure to the battery, which has a positive voltage to the right and negative voltage from left, uh, we'll get that the electrons from n-type semiconductor will flow to the right and the holes will flow to the left. So this way the depletion layer will expand, eventually acting as an infinite resistor. But if we inverse the voltages so that the positive voltage from the in the left and the negative in the right, we get that electrons from n-type semiconductor will flow to the left and p-type and holes from p-type semiconductor will flow to the right. So the depletion layer will disappear. So this configuration that allows the flow of electrons to only one direction, that is from n-type semiconductor to p-type semiconductor, and this element is called diode because it one more it blocks the flow of electrons from p-type to n-type, but enables it from n-type to p-type. So transistors and configurations of transistors. The most widespread configuration is bipolar transistors that consist of 2N and 1P, or 2P and 1N semiconductors, this way presented in the screen. So let's review this case. When a transistor is connected from the P side and N side to a battery, which has negative voltage here and positive voltage here. In this case, the flow of electrons and holes is free, and they freely flow. However, if we connect a stronger battery here, we'll get that uh, there is a flow of electrons flowing this way a little bit. Uh, Here, there's between these p-type and n-type semiconductors, there was a depletion layer that didn't let the electrons to flow this way. But in this case, when also this side of n semiconductor is connected to electricity, is connected to positive voltage, because the holes that are moving this way, not only the holes that are in the depletion layer go away from it, but this also provides a new fresh supply of holes uh, that can be filled with electrons. So the electrons from this p-type also can jump to this n-type and flow here. So these configurations creates a little flow of electrons in this circuit and a massive flow of electrons in this direction, like this. So here, this is a transistor. It's basically an amplifier, and this n-type semiconductor is called emitter. This is the base, and this is the collector. This is an emitter because it emits the electrons to the right side, and collector because it collects the electrons emitted from the emitter. And base, it's called so because it controls the flow of electrons. If there was no voltage here, the electrons would not flow this way. So proceeding to the next topic, logic gates. Logic gates are based on Boolean algebra. Uh, this allows us to represent logical operations in digital electronics. So what's Boolean algebra? It's an algebra that uses only two values, true and false. This is the most appropriate for building communication between us and computers, because computers can only understand electricity. And how can we communicate by using only electricity? Okay, the electricity is either exist or no. It flows or no. So the state of flowing is denoted by number one, and the state of no electricity is denoted by number zero. So these logic gates process these numbers and binary blocks inputs to produce a single binary output. Uh, Even which this makes them essential for computing and decision making in electronic systems. So here we see the logic gates that each performs is distinct function, and it each gets two inputs except not, and outputs one output. So not gate, it has one input and one output. Basically, it's a negation. Uh, so this is the truth table for it. When you have zero in output, we have it inverts it to and outputs one. And when the input is one, the output is zero. The NOT gate, its operation is denoted by a this way. So let's review this circuit. Here we have a 5 voltage on the upper, uh, and after it we have a resistor. The output is before the transistor itself, input to the transistor, and it comes to the ground that is has zero voltage. So in this configuration, let's review the cases one by one. In case the input is zero, there is a zero voltage here. So the transistor is open. There is no current flowing this way. So because of this 5-volt voltage is also applied to the output, and it has positive voltage, and its output is 1. But when the input is 1, the transistor is closed. It means that the current this way is enabled. And in this case, the difference of potential between output and the ground is zero. So the output voltage is also zero. If you don't understand, it's normal. You don't need to, but you do just need to understand the main principles and logic, how it works. So just remember that NOT negates the input and outputs the inverse value. So AND gate. Let's first review its truth table. Here we see for each output, uh, it outputs for each input. Firstly, it takes two inputs, unlike the NOT gate, and it only outputs one when both the inputs are one. So this is a representation, a symbolic representation of AND gate's function. And in the same circuit that in this case we placed two transistors consecutively, and the output and the resistor after them. So when in the case when both inputs are zero, so both transistors are open, there is no current flowing uh, through them. So the output is zero. When only one of them is closed, and so the current from here to here is enabled. Yes, but this transistor is open, and there is no current through it. So in this place of the circuit, the voltage is also zero. When this one is closed and this transistor is open, when this input is 1 and this is 0. So the current to this point is enabled, but the electricity can't go through this transistor, because it's open. So again, the output is 0. But in case when both inputs are 1, are positive, and both transistors are closed, there is a current. So the 5 voltage here applies also to the output, because of difference of their potentials. So the output is 1 in this case, only in this case. Okay, OR gate. The truth table for OR gate is the following. Here we see that the inputs are similar to the AND gate, but here the OR gate outputs 1 in all the cases except for the case when both of the inputs are 0. So this is a functional symbolic representation of OR gate. And in this circuit, we see that uh, both of the transistors are connected to the 5 volt wire and to the output. In this case, when both of them are open, that is the inputs are zero. There is no current flowing from here to here, and no current through this transistor. So the voltage on the output is zero. However, when, for example, in this case, the input to this transistor is zero. It means it's open. There is no current through it. But this transistor is closed. Its input is 1. There is a current of electrons through these. And also because of, yeah, this is also connected to the output. The output voltage is positive. The output is 1. In case this transistor is closed and this one is open, uh, the current from through this transistor is blocked. However, the current through this is enabled, so the electricity comes through this to the output, and the voltage output here is positive, that is 1. And in case both transistors are closed, so the inputs are 1, we see that um, from both transistors there is a current flowing to the output, so that the output is basically 1. Hmm. XOR gate. This is one more complicated, and however, this is one of the most essential and vital logic gates, which we'll explore later in the next topic. So the truth table for this XOR gate outputs 1 when only either of the inputs is 1. So when both of the inputs are 0, the output is 0. When either of inputs is 1, the output is 1. But when both of the inputs are 1, the output is 0. So this is the symbolic representation of XOR gate. So we see here a familiar symbol here. And I forgot to mention that all these gates and or have their negation, and that is their negated variant outputs the inverse value that the usual one outputs. So the here or this is the negative variant of or is nor. This one. It has a little circle here that represents that it's negated. So it uh, outputs only 0 um, in all the cases that all output 1. So let me show. The NOR gate would output 1 when the two inputs were 0, and okay. Wherever you see 1 in the OR gate, the NOR gate would output 0, and when OR gate would output 0, the NOR gate would output 1. So when the two inputs are 0, the NOR gate would output 1. When inputs are 0, 1, the NOR gate would output 0. When inputs are 1, 0, the output is 0. When both of the inputs are 1, the output is 0 for the NOR gate. So the NOR gate is different from the usual OR gate, just with an additional NOT gate here on the output. So you just use this configuration to the end of the output of OR gate, and we get an NOR gate. So when OR gate has two transistors in it, then NOR gate would have three transistors in it. And the same logic for NAND gate. It also has a little circle here that represents that it's a negated variant. And the NAND would output 1 when both of the inputs are 0. When inputs are 0, 1, it would output 1. When inputs are 1, 0, it also outputs 1. But when the inputs are 1, 1, the output is 0. The inverse values of the AND gate. So here, the XOR gate. We recall that this is the truth table, and let's review each case and see that this configuration is the true for XOR gate. In case when both inputs are 0, the A is 0, the B is 0. A comes to here and B comes to here. 0, both are 0. We call that AND gate. When inputs are both 0, the AND gate would output 0, but the NAND gate outputs 1. So the 1 goes here and here. In this gate, the inputs are 0 and 1. AND gate would output 0, but the NAND gate outputs 1. And here also, the inputs are 1 and 0. The NAND gate also outputs 1. And here we have 1 and 1. And because NAND AND gate outputs 1 when the inputs are 1, 1, the NAND gate returns the inverse value, that is 0. Here we get 0. We see that it's true. In case 0, 1, A is 0, B is 1. Here input is 0, 1. The NAND gate outputs 1 because AND gate would output 0. A is 0 and this way is 1. 0, 1. And AND gate also outputs 1. But here B is 1 and this way is also 1. Now this NAND gate would output 0 because both inputs are 1. So this output is 0 and this one is 1. So when the NAND gate has inputs 1 and 0, it outputs 1. We see that it's true. So the same logic will be with the inputs 1 and 0. And in case both inputs are 1, let's see. A is 1, B is 1. Here we have 1, 1. The NAND gate would output 0. So here, 1, 0. The NAND gate, the NAND gate outputs 1. In this gate, we have 0 and 1. It outputs 1. We have here 1 and 1. So the NAND gate would output 0, as shown here. So this truth table is true, and this circuit is also true for XOR gate. Let's proceed. Combinational logic circuits. Okay, these circuits play a crucial role in performing basic arithmetic operations such as addition and subtraction without relying on memory. So they use no memory and operate on their instant values. We'll be looking at two important types, full adders and full half adders for addition, and half subtractors and full subtractors for subtraction. These circuits are designed to process inputs and generate outputs instantly based solely on the current values. Understanding these circuits will give us a deeper insight into how computers perform binary arithmetic. Let's start. So, how we do binary addition? In this example, we see that we can build a truth table for addition. So when we denote the addition is fulfilled in this way. We take into account only a one column of numbers. So we see only this one and this zero. The rest of the numbers are not significant for us. So we denote them from with A and B. So when the inputs are 0 and 0, what would you think the sum would be? The sum is 0. And we call that carry uh, is when we have a sum that is bigger than a 1, where we need to carry the value to the next operation. So see, here we have 1, 1. But after 1, we don't have digits in binary numbering system. So here we write 0 and carry 1 to here. Here instead of 0, we have 1. And plus 1, we get 0. And 1 carry. We carry that here. We have 1 and 0. Their sum is 1. But the carry with the carry that is 1, the sum would be 0 and carry 1. And the carry is written here. So this truth table represents all the operations we do here. And we would like to build some logic using logic gates that would perform addition that with having only these two numbers, these columns, two numbers, and the carry. So for building it, we need to know which logic gate we will use for it. So let's see the truth table for sum. Does it remind it to something? Isn't it? Oh, no. Isn't it similar to the XOR gate? We get zeros when the inputs are the same here and here, and one when the inputs are different. So for representing sum, we will use the XOR gate, and for carry, we have one only in the case when both inputs are ones. And this is similar to the AND gate. When in all cases we have 0, and when both inputs are 1, we have 1. So the circuit for addition would be something like this. A and B are the numbers. So they're the A and B are processed through XOR gate. This would output the sum. And also we take the values of A and B and give it to an AND gate that would output the carry. However, this circuit is not complete because it doesn't take into account the carry that can be produced from the previous operation. So this is called half adder because it performs only the half of the operation. But to have all the operation performed, we need the full adder. So, but first let's take a look at the truth table of full addition. Here we also have the third input, carry in. It is the carry that we have produced from the previous operation. So you can pause the video and review it yourself, but here we will do it very quickly. So when the carry is One is just an additional uh, addition, if you can say it so, with the number. So first we add um, the A and B, and then we add their sum to carry in. So when the A and B are zero, the carry in is one, the sum is one. And however, when A zero, B one, but the carry in is one, we get that the sum is zero because we add 0, 1. We get 1, 1 and 1. We get 10 in binary, but we write 0 and have 1 in carry, as here. However, in case when both A and B are 1 and the carry in is 1, we'll get that 1 plus 1 is 10 in binary. We have 0 and 1 in carry. But when we add the carry into it, we get 11 in binary, which is 3 in decimal, by the way. And the digit we would write in the normal addition we do it as here, we would write just 1 and carry 1. So you get the idea. This is the circuit for full addition. A and B are processed through XOR that outputs their sum. Their sum is also processed through XOR with carry in, which outputs the sum that also takes into account the carry in. And these AND gates output the carry out for both of the operations, addition operations that perform the XOR gates. And we just need to take the if either it exists. So if just only one would be would output carry out, we need to take it. So the OR gate is perfect for this. Let's review this in example. Let's take this case when A is 1, B is 0, and carry is 1. So A is 1, B is 1. Oh, no, A is 1, B is 0. XOR outputs 1, but AND outputs 0. The carry for only this operation would be 0. So their sum is 1, and when we take into account also the carry in, which is 0, the sum of A and B and carry in would be also 1. Oh, the carry in is 1. Oh, sorry, I messed it up. So the sum of A and B is 1, the carry in is 1. The XOR output 0. The last digit of the sum of carry in and the sum of A and B, which is 0, as here. And we also have the carry in is 1, XOR outputs 1. So the carry of this operation is 1. Recall that here we got a 0 and here is 1. So the OR gate outputs 1. The carry for this whole operation, the carry out is 1. And the other case, like this one, the last one, when all the inputs are 1. So A and B are 1, XOR output 0, and AND outputs 1. The carry is 1. And carry in is 1, and XOR output 0. So this XOR outputs 1. 1 for the whole operation. The sum is 1. But here the XOR output is 0, and carrying is 1. The AND gate output 0 because the XOR output 0. And recall that here we got 1 and here is 0 coming. The OR would output 1. The carry out for this whole operation is 1. So you see that this circuit is performing very well and perfectly match our uh, operation. Oh, so we will denote the half adder this way and full adder this way. Half adder takes two inputs A and B and outputs two values sum and carry. But the full out adder also takes into account the carry in, so it has three inputs and two outputs. And you see that half adder, uh, we see the structure of XOR and AND. And in full adder, we see two of these. So the full adder basically consists of two half adders connected with OR gate. The half adders output the sum of each part of the operation, and we combine the and get the combined carries using the OR gate. So if we want to do addition of, for example, 3-bit binary numbers, we would like to have three full adders, one for each column. You see that, for example, uh, this here, the first column is 1 1. The first full adder gets inputs 1 ones. Because this doesn't have any carry, the input for carry is 0. Uh, the second one, here the full adder will output the sum of 0 and carry 1. Here, the second column, A is 0, B is 1. The inputs are 0 and 1. And carry in is 1 from the previous operation. The sum of all this is 0, carry is 1. And here we have A is 1, B is 0. The same sum is 0 and carry is 1. So it's a return in this direction from 1 to 0, 0, 0. Okay. Subtraction. Subtraction is somewhat similar to addition because here you see the truth table. You see that when we subtract 0 from 0, 0, we get 0. But here we also have the concept of borrowing. Borrowing is when we uh, uh, take the value from the next column, from the number from digit in the next column, and uh, because the divider is bigger than the dividend digit. So when we can't subtract from 0, 1, so we take, for example, in this case, uh, let's proceed here, and in the third column, the 1 can be subtracted from 0. So this 0 takes the value of the left hand column, uh, and it because this one mm, uh, is like the 10 for the previous column. Instead of this 0, we have 10, from which we subtract 1. And in this case, the output is 1. So the difference is 1. But we borrowed 1. And in case 0 is subtracted from 1, the difference is 1. And when 1 is subtracted from 1, the difference is 0, borrow is 0. So here we also see that this difference truth table is uh, similar to the output of XOR gate, so we'll also use XOR. But borrowing is somewhat different because here we see that the we get one, the output is one only uh, when the first input is zero and the second one is one. So we can, for example, we can negate this input, the first input. We will get 1, 1, 0, 0. In this case, this would be something similar to AND gate because 1, 0, output 0, 1, 1, outputs 1. What we need to. So here we negated this one. And so this is 0 and 0. The AND gate output 0. And 0, 1 and get it output 0. So perfect. We already know the logic for this. So let's perform it. So A and B are connected to our XOR which outputs the difference. Oh, it seems that I made a mistake while making the slide. Sorry for this. The NOT gate, but it's important to emphasize, the NOT gate must be connected to the first input. First input is the digit that is being subtracting from. So in this case, A is being subtracted from. So this wire should have been got from A. So I made a mistake. So, but we can just dismiss it. So A, in this one we have A. This is B. We need to remember it. And let's review this in cases. Let's review this the first case. Both are zero. When both are zero, the XOR output zero. But when A is zero, the node inverts its value so that we get one here. The B is zero. So AND gate, when it has inputs 1 and 0, outputs 0. True. So the second case, A is 0, B is 1. The XOR outputs 1, and when A is 0, we call that A is this one. The node gate inverts it and we get 1. B is 1 also. So the AND gate would output 1 because the both inputs are 1. The third case, when A is 1, B is 0. XOR outputs 1. We know this. So A node negates A, we get 0 here, and B is 0. So the AND gate output 0. And in the case when both inputs are 1, A is 1, B is 1, XOR output 0. A is inversed to 0, B is 1. So the AND gate output 0. So these circles perfectly matches our truth table. And we can use this. And similar way, uh, yes, a similar way for full subtraction is I made the same mistake here. Please remember that the NOT gate should be applied to the input that is being subtracted from. In this case, A is being subtracted from, and this wire should be connected to A, not B. So what we get here, uh, this was a half a subtractor because it doesn't take into account the borrow that we get from the previous operation. But here we have borrow in, which means that the number was borrowed from during the previous operation. So when there is borrowing when A and B are 0, This means that we can't subtract 1 from 0 from A. So we need to borrow uh, from the left column, from the next digit. We have borrow out here 1, and when we borrow from the next digit, we get 10 being subtracted. We get 10, and we subtract 1 from this 10, and we get 1 difference. So this is a similar to the how we get the full truth table for addition. Also, you just can pause it and check it for yourself. And only the I'm going to review the some of the cases. But before cases, we see that also this XOR gate uh, is connected to NOT gate here. Here I did it very correctly because the XOR gate outputs the difference of A and B, and which also needs to be also from which we need to subtract borrow in. So we subtract from the output of XOR the borrow in. In this case, the output of XOR is a dividend. Borrow in is the oh, is the borrow in is the subtractor. The output at XOR is a number that is being subtracted from. So we need to uh, negate the input that is being the output that is being subtracted from. So let's review the case when A is 1, B is no, let's take this one. A is 0, B is 1, and borrow in is 1. Okay, A is 0, B 1. The XOR outputs 1. So we remember that this wire is connected to A, not B, and this one is connected to B. So A is 0. 0 is negated, we get 1. And B is 1. So the AND gate outputs 1. This is the this represents the borrow that we should get from this operation only. But when we have XOR output with 1 and borrowing is also 1, this XOR outputs 0. This input, the output of XOR is negated, so we get 0, and borrowing is 1. The AND gate output 0. So we recall that here the AND gate output is 1, and here we have 0, so the OR gate would output 1. And the difference for the whole operation is 0. How do we get this? Because we can't subtract from 0, 1. We borrowed from the next digit and we got the 10 in the place. From 10 we subtracted B. We got the one the digit 1 remained. And from the 1 we subtracted a borrow in. And the output the difference is 0 right here. And also let's review this case. A is 1, B is 1, borrow in is 1. So A and B for the XOR is 0. We call that A is this one. A is negated, we get 0. And B is 1, so there's 0 and 1. And the output 0. So borrow in is 1. The output of XOR is 0. This XOR outputs 1. The difference of the whole operation is 1. So, but the XOR's output 0 negated is 1. Ball in is 1, the AND gate outputs 1. So here you get that this AND gate outputted 0, this AND gate outputted 1. So the OR gate outputs 1. As we here see here, the ball out is 1. So let's see. Also denote the half subtractor this way that takes two inputs and gives two outputs. Two inputs the digits and the outputs are the difference and borrow out. The full subtractor gets three inputs. It takes into account the borrow that uh, was produced in the previous operation and also outputs two values, difference and borrow out. So as with the full adder, we can see that this construction of half subtractor is repeated two times in the full subtractor and connected with OR gate. So we can represent full subtractor this way. This is these are half subtractors connected with the OR gate. So this is the circuit for performing a 3-bit subtraction. And again, for each bit, we have one full subtractor. In this example, see, we have 101s and from 101 subtracted 0, 1, 1. First column, 1 and 1. The borrowing is 0 because we don't have a value here. So inputs are 1, 1. The difference is 0. Borrow out is 0. Second column, 0, 1. The borrowing is 0 and the values are 0 and 1. 1 is subtracted from 0. So we get here borrow out of 1 and difference 1. In third column, we have A is 1 and B is 0. 0 is being subtracted from 1, but borrow in is 1. So we get the difference is 0 and borrow out is 0. The outputted number is 0, 1, 0. That's 10 in binary and 2 in decimal. Okay, that's it. That's for today's video. And thank you for watching. And I hope this was helpful for you and you understood my explanation. Please leave your feedback in comments. And I will be very grateful for it. And that's it. Bye bye.